All right, and we're back, and we're going to move into talking about global pressure. So there are general patterns of high and low pressure around the world. We've talked about, patterns of winds, patterns of the subtropical highs, and the vertical movement of air. But there are also global air pressure systems, and these are seasonal. They shift in large part because of our seasons, right? So areas of high pressure, right? So high pressure needs warmth. So areas that get warm, like the ocean in the summer, have areas of lower pressure. Areas that are colder, like say the poles, have high pressure. And so these drive these global pressure systems north and south. So in the northern hemisphere, all systems move north in the summer and south in the winter, right? And these also control rainfall and snowfall, and this whole pattern is why we have, rainstorms in the summer, snowstorms in the winter. And as you can think, when it comes to, precipitation, that affects vegetation, right? So just kind of an idea here. Talks about how at different times of the year, these are dominated by different things that we'll talk about, like the polar high or the Bermuda low. So let's start about this. We know that land heats faster and cools faster than water, right? So what happens is in the summer, areas over land get hot faster. And so if the land is hot, it heats up the air. Remember, hot air expands. So we find in the summer low pressure systems over land, comparatively higher pressure over water, right? So one of these most famous ones is called the Bermuda High. And you're going to learn about that in one of your movies that you have to watch if you haven't watched it already. The Bermuda High helps drive the path of hurricanes. Okay, so here's a couple examples. This right here is January. So in January, right, it's cold over North America. It's winter. So we have the Canadian high, right, or the Siberian high, which we'll talk about here. Very high pressure here. But in the southern hemisphere, it's summer. So here, right, it's warmer over land, so you have low pressure over land and high pressure over the water. Okay, you see the ITCZ is further south. Now, let's move ahead 6 months, and this is July. And now in the northern hemisphere, it's summer. So right here, right, the land area heats up much higher, so you have low pressure over North America and Asia, and higher pressure over the ocean. So you have the Bermuda High right here. Higher pressure here and lower pressure here. And this helps drive weather patterns. We're going to get into that a little bit later. Now the next wind system that we'll talk about, these are the ones that aren't affected so much by the global patterns, but more local things like sea breezes. And it goes back to that whole idea of scale, synoptic scale. When we look at things in space and time, right? Temporal scale, how long does something last? How long does a weather event last? Does it last hours? Does it last days, weeks, or months? So there are various things. A tornado lasts a couple hours. A thunderstorm can last half a day. A hurricane will last 3 to 4 weeks or a month. Different things. The Asian monsoon lasts half a year. We also notice in the size of things. And generally speaking, when we go from micro scale, the small end of the area. So valley and mountain breezes happen on the time span of hours, and they only cover a very small area, maybe a couple of kilometers wide. Whereas an Asian monsoon or a hurricane, which may take weeks or months, can be thousands of miles wide. So as the temporal scale increases in duration, the spatial scale of size increases. So, sea and land breeze. A sea breeze is quite simply, besides a name for a drink, right? If you are near the ocean or near a large body of water and the wind blows over the water onto land, it's a sea breeze, and it's usually cooler. We call it in here a lake breeze. If you've ever been towards the lakefront in summer and you feel that cool air, that's a sea breeze. The exact opposite is a land breeze, and that's where the wind blows from land onto water, and that usually happens at night. So if you've ever been at the beaches at night, maybe you've noticed the wind blowing from your back. Okay. Now we see it mainly in the tropics just because there's so much more water and so much more heat. But what causes it here is, we'll just say this is Puerto Rico, right? So in the daytime, the sun warms the land faster. And so the warm air, or the land gets hotter than the water quicker, which warms the air, and then that causes low pressure, right? And which means that the water over the air is higher, or the air over the water is higher pressure. So remember, air always goes from what? High to low. So it drives the breeze this way. The wind's going to blow this way. So high pressure, cooler air blows onshore, an onshore or sea breeze. But at night, the exact thing happens. After the sun goes down, the land cools off quicker. So the air cools quicker. So this air rises in pressure faster than here. And so now this has a higher pressure than here, and the winds go backwards. And so basically every 12 hours, back and forth, back and forth. Now the monsoon, the Asian monsoon, this affects the continents that surround the Indian Ocean. So we're talking East Africa, Pakistan, India, Myanmar, Thailand, and Australia, all the way around. This is basically a very large version of that happens over the course of months. It's a seasonal pattern of winds that also brings moisture with it. So it's created by the ITCZ, but it's also influenced by the Himalayas and the heating of the Asian landmass. And what happens in an Asian monsoon situation is that your summer is warm but wet. The winter is only slightly cooler but much drier. So here's what happens. In the summer, we know the ITZ moves north. And so here's that band of thunderstorms. And here you have, right, high pressure over the water and low pressure over the land. Remember, the land heats up, so this is very low pressure. So what happens is the air flows this way towards the low pressure. So you have all this air flowing over the Indian Ocean. It's warm, it has a lot of moisture. It flows right here, so warm, wet air. But what brings the rain is as it goes inland, when it hits the Himalayan mountains, it goes up in altitude by about 4 miles. And so that orographic lifting pulls all the moisture out right here. And by the time it gets here, it's very dry air. Now, in the winter, it reverses. So now it's cooler here in Siberia. So now the air pressure here is much higher, which drives the air from this area of high pressure towards the lower pressure over the area of the ocean. So now the winds come this way. They blow south. But they're coming here where it's dry. So there's no moisture. So as they go towards the ocean, they're a little bit cooler, but much drier. Okay? So these dry breaks can last a few weeks to a month. But they're a very predictable pattern, and most of the farmers know when it's dry, when it's wet. But because it is not perfectly predictable, if something happens, if the temperatures are changing, it can make this occur longer, shorter. If it happens where the dry periods last longer, you can have droughts. And if you have it too short, when it rains too much, you have flooding and erosion. But millions of people are affected by this. Valley and mountain breezes are kind of like onshore, offshore. They happen in a very local area, and they happen back and forth over the course of a day. But here, instead of water and land, you have a valley or a mountaintop, and then low land. And what happens is you have a valley breeze that blows up the side of the mountain during the day, and then a cool breeze down the valley at night. So here's what it looks like. Here's a valley, and you have the mountains here. This area gets hot faster because it's up higher, closer to the, there's not as much to surround it. So this gets hot faster. So the air pressure here, right, it has lower pressure, which pulls the breeze up. But at night, it cools off faster. Denser air cools down. So it's a warm breeze in the day going up the side of the valley, and a cool breeze at night. Another variation of that kind of process are what we call the Chinook and the Foehn winds. And these are winds that flow up or down the sides of mountains, but very local. The Chinook happens in the Rocky Mountains. These are warm, dry winds, and they flow downslope. So what happens is, remember how when the wind hits the mountain, it goes up, and it cools, and it loses all its moisture. And then when it comes back down the mountain, it's dry. And what happens is, when the weather patterns are right in the Rocky Mountains, these Chinook, warm, dry winds come down the side of the mountain. They're very dry and very warm. And if it's a early spring and this happens, it can melt the snow because the temperature will go up to almost 20 degrees, literally, in a matter of hours. So it may be 20 degrees when you go to school, and by lunch it's going to be 45. And because the temperature changes so quickly, once in a great while you'll see snow melt or sublimate where it goes straight from being a solid to a gas. Okay, same type of structure. If it happens in Europe, they call it the Foehn winds, and this happens in the Alps, which is where Austria, Switzerland, Italy are. So it's a downslope wind. So again, remember, you have the situation where air comes up the side of a mountain, orographic lifting, loses all that moisture, so that when it comes back down, it's dry, and as it comes back down, it is compressed by air pressure and becomes very warm. So this would be a Chinook or a Foehn wind. Last one that we'll talk about before we finish the chapter, the Santa Ana winds. Santa Ana winds. Again, same thing. It's downslope winds, right? Now this occurs in California, hence the name Santa Ana. And what happens is it's kind of like that mixture of the monsoon slash the downslope winds. They're hot, dry winds. And what they're very famous for is that their wind speeds can be almost 60 miles an hour. So it's this hot, dry, extremely fast wind that happens to blow through the mountains in California. At the same time of the year, it's the dry season. And so if there's a forest in California that's really dry, this dries out even further. And what really will happen is if there's a wildfire, a small fire starts, and these winds kick in, it can make these wildfires just explode. If you've ever blown on a campfire when you were a kid, right? So you get it to blow, it's the same thing. And here's how it forms. In the winter, right, it's cooler over here, over Utah, so we have high pressure. And there's lower pressure here off the ocean. So again, you have that difference. And so the air wants to flow from high to low. But as the winds blow across the surface, there's a series of mountain ranges right here, like walls. And when they get down here, there's a couple of valleys that kind of act like holes in the wall. And it channels these winds. And so these winds start blowing, and they get basically channeled into these narrow valleys and just come roaring out. All right. Now the Katabatic wind, this is the last one. This is the odd one. This is gravity. And it forms in a very unique place, basically Greenland and Antarctica. This is gravity winds. So Iceland and Greenland Greenland and Antarctica are covered with ice. We're going to talk about that in a little bit. But the ice and the glaciers can be 2 to 3 miles thick. So that means that the air on top of the glacier is at an altitude of 2 to 3 miles. So it's very, very high altitude, right? But it's very, very, very cold. And cold air, in fact, some of the coldest air in the planet is there, which makes it extremely dense. And dense air weighs more than less dense air. If the air gets to the edge of the glacier, it basically rolls down the side of the glacier, and the gravity forces it to come down. And what happens is, this wind can be stronger than a hurricane. We don't really talk about it too much because it happens in Antarctica, and who lives there? So right here, this is the ocean. Here's the coast, and these are cliffs. This right here is about 2 miles up in the air. This ice is 2 miles thick. When it cold, when it hits the edge of these cliffs, it literally just gravity rolls it right down the hill, and it comes down so fast. Katabatic winds. So this was one of those chapters that I know a lot of terminology, a lot of processes. But now what we're going to do here is this is giving you kind of the foundation for the next thing. Now we're going to start talking about the exciting stuff like hurricanes and tornadoes and thunderstorms, because now you know the processes behind these. So that when we talk about how do hurricanes form and we discuss latent heat, you know what that means. And going forward for the rest of the semester, that's the way these kind of work. With this part of the textbook, the first part was the atmosphere. We start with the basic building blocks, how they build, how they interact, so that you kind of have an understanding of all the processes. And then we apply it to things like storms. So the next chapter, when we talk about volcanoes, we're talking about rocks and chemistry first. So for those of you who stuck with me for this, great, thank you, I appreciate that. And for those of you who didn't watch it, well then, whatever.